All right, welcome back everybody. In this video we're going to continue with section 8.4 of AP Calculus, finding the area between curves with respect to x. And so we're going to pick up right where we left off. We just finished example 2 at the end of the last video, so we're going to finish up with the last few examples of this lesson in this video. So let's start with example 3. Find the area of the region in the first quadrant bounded by the curves y equals x squared, y equals 8x, and y equals negative x plus 7. To help me see what this looks like, I'm going to have my calculator help me out here. Y equals x squared, y equals 8x, and y equals negative x plus 7. And we'll go ahead and graph that. All right, there's our parabola. There's y equals 8x, and there's y equals negative x plus 7. Okay, so let's think about what this region looks like and how we're going to handle finding the area of this region. Okay, so we've got parabola y equals x squared. We've got y equals 8x. Sorry, my hand's a little wobbly sometimes. And we've got y equals negative x plus 7. There are all the curves that form this region. Now, something that's different about this region compared to every region that we've looked at so far is that as we look at this region, the top boundary of this region changes. So if you look at this, the bottom boundary of this region is always the parabola. The bottom edge of the shaded region is always the parabola. But the top edge of the region changes, where initially it's the line y equals 8x, and then it transitions, and the top part of the boundary is y equals negative x plus 7. What that means is that it's going to require us using two integrals to find the area of this shaded region. We're going to have one integral that does everything to the left of this blue vertical line, and we're going to have another integral that gets all the area to the right of that blue vertical line. All right, so let's start setting this up. We're going to have the integral from 0 to something. I'll find that something in a second. Well, not in a second, but in a few minutes. The upper boundary of that portion of the region is 8x, and the lower boundary is the parabola. Okay, that takes care of everything to the left of the vertical line. And then I'm going to add to that everything to the right of the vertical line, which is going to be the integral from whatever this x value is, and my all the way up to this point right here, the x value there. But now my upper boundary is negative x plus 7. My lower boundary is still x squared. So that's what my integrand is going to look like. And now all I need to do is get myself some limits of integration. So let's find some intersection points here. I want the intersection point of the two lines first. That happens at 0.7 repeating. Or, you know what, I'm going to write that as 7/9 instead of as a repeating decimal, because it's easier for me to put 7/9 into my calculator. And then, let's see, my other intersection point I need is this one right here. So let's set that up. Let's get an intersection point parabola, and this line. And those two intersect at 2.1925824. All right, and now that I've got all of my limits of integration, I'm going to go ahead and just calculate this using my graphing calculator to help me with the integration. So I'm going to take the integral of 8x minus x squared, sorry about that, 8x minus x squared with respect to x from 0 to 7/9 plus the integral of negative x plus 7 minus x squared, also with respect to x, from 7/9 to 2.1925824. My calculator tells me that this is 6.709. 6.708 also acceptable as the area. All right, so sometimes we might need to break a region down into multiple regions based on the transitions in what forms the upper boundary of the region and what forms the lower boundary of the region on those particular intervals. All right. Example 4 from the 2001 AP Calculus AB exam free response question number 1. I don't think I'm going to get through all this video. Example 4 from the 2001 AP Calculus AB exam free response question number 1. This is a calculator active free response question. So we've got let R and S be the region in the first quadrant shown in the figure to the right. The region R is bounded by the x-axis and the graphs of y equals 2 minus x cubed and y equals tangent of x. The region S is bounded by the y-axis and the graphs of y equals 2 minus x cubed and y equals tangent of x, as you see in the graph over here to the right. First, we're going to find the area of R. Okay, and again, for R, the x-axis is the boundary, so really we're just finding the area underneath one curve. But we've got a transition of boundaries here again, so it's going to require two integrals. We've got one interval where the tangent is the upper boundary and one interval where the 2 minus x cubed is the upper boundary. So we're going to set up two integrals. Integral of tangent of x dx plus the integral of 2 minus x cubed dx. And now we just need limits of integration. We've got 0 as the first limit of integration. And then I'm going to need, and this is a calculator active question from the AP exam, so I'm going to go ahead and graph these two equations in my graphing calculator in order to find my intersection points. So I've got y equals tangent of x and y equals 2 minus x cubed. We look at our graph. I'm going to zoom in on this. All right, let's zoom in. Because we're just looking at this piece of the graph right here. All right, so I need that intersection between the two curves. That happens at 0.90215. 0.90215. 505. So that's the upper limit of integration for the first integral and the lower limit of integration for the second. And then the upper limit of integration for the second is going to be this right endpoint, which is the 0 of the second curve. So I'm going to go ahead and calculate that, the 0 for not the first curve, but the second curve. And I find that that's 1.259921, 1.259921. And so now we're going to go ahead and calculate those using the numerical integral. And so we've got integral of tangent of x with respect to x from 0 to 0.902155505 plus the integral of 2 minus x cubed with respect to x from 0.902155505 to 1.259921. And I get 0.729 as the area of this region. Okay. not sure if I have quite enough time for part B, so you know what we're going to do? We're going to cut off this video right here, and we'll come back and do a third video on this section where we find the area of region S in this picture, and where we do example 5. Okay, so see you then. Have a great rest of your day, everybody, and enjoy yourself. Bye-bye.